right? Now assume you have a continuous mass distribution like this, which is in the form of a rod. If it's a uniform rod, you know where its center of mass lies. We had discussed that in the last class, that is the midpoint. Suppose this rod's mass density, linear mass density, varies from point to point. Okay, let's say lambda is equal to 2x. Okay, where lambda is nothing but linear mass density, that is mass per unit length. Now, the rod is placed along the x-axis. Different particles of the rod have different x coordinates. Fine. Now, based on the x coordinate of the particle that you select, its mass density will change. Means the density of particles is different from position to position. The density of particles varies from position to position. That is what this means. Okay. One of you tell me, which side of the rod is heavier, the right side or the left side? Which half of the rod do you think is heavier? And why?
Right side.
Right half is heavier. Okay. Aishwarya, how do you justify that?
So the value of x keeps increasing.
Yes, the right side half has higher x coordinates, greater x coordinates. And if x coordinate is greater, density will be higher. Okay, so more mass lies on the right side, in the right side half of the rod. Fine. And the mass goes on, not mass, the density goes on increasing as you move to the right, because the linear mass density function is like that. Fine. Now try to guess. Will the center of mass of this rod, of this non-uniformly distributed rod, lie at its midpoint, or will it be to the left of the midpoint, or will it be to the right of the midpoint? We know that the mass density increases as we go to the right side. So as you move to the right side, as you move from x is equal to 0 to the other end, density of the particles increases. So do you think the center of mass will lie at the midpoint, or in the right half, somewhere in the right half, or somewhere in the left half?
Right half, sir.
Right half, obviously. Center of mass is closer to the heavier mass always. Okay, fine. The question is to find out the position of center of mass of this system. Now clearly this is a continuous mass distribution and all the particles lie on the x-axis. So all you need to find out is the x coordinate of center of mass. Can one of you quickly tell me the formula for x coordinate of center of mass of a continuous mass distribution?
Integral x dm by integral dm.
Integral x dm divided by integral dm. Good. So how do you start solving this problem? You have to consider the rod as a collection of particles now. So you have to visualize a particle. See, visualization is the first thing you need to do in any physics problem. In fact, we have done some of that already. Instead of blindly writing the formula, we imagined on which side the center of mass could lie. Okay, which side of the rod is heavier, which side the center of mass could lie, all that we considered. So that kind of understanding should be there. After that, you apply equations and solve. Okay, so to begin, you have to choose an element first. Okay, rod is a collection of particles placed one next to the other. So take a random particle somewhere here. Remember, the random particle that you choose should never be the first one or the last one. Okay, because you'll tend to make mistakes. Suppose you take the random particle as the last particle. What you will do, you'll write its x coordinate as 2. We know that for the last particle x coordinate is 2. So you'll have a tendency to substitute 2 here. For the last particle, that's okay. But for other particles, x coordinate is not 2. So you have to choose a random particle for which the coordinate is a variable, unknown. Okay. So generally also while integrating, never take the element at the extremes, the first element or the last element. You have to choose a random element in between. So let's consider some mass of the rod like this, which is dm. Okay. And its x coordinate should be assumed. Let it be x itself. If you take it like this randomly in between, you'll understand that from element to element, the x coordinate will change. Okay. And you won't know its x coordinate, so you'll substitute x only in the integral instead of substituting 2 or 0. Okay. Try this, all of you. To integrate xdm, I hope you remember what you need to do. To perform this integral, you have to express dm, that is the mass of that small element, in terms of dx. And what is dx? Dx is going to be the length of that small element. Okay. Try this, all of you. I'll give you 3 minutes. Right. Any answer, any of you?
So 2x by 3.
Substitute limits, no? You know from which x coordinate to which x coordinate the rod lies. So finally, the answer will be a number, like some distance you will get. Okay. Maybe if you put x as 2, your answer is 4 by 3. 4 by 3 is more than 1. So it's in the right side, right half of the rod. We'll see. We'll see. Others, any answer? Pawan?
No, sir.
Okay, Pawan, tell me what you tried to do. Were you able to write any steps?
Sir, dm dx ఇక్కడ మస్కల అర్థం కావట్లేదు.
Okay. What is the meaning of dm?
Mass of that small
Mass of the
particle.
mass of the particle, mass of the element. Correct. What is dx? Length of the
దాని
element.
small
Length of the small element. So you have to relate its mass to its length. And that is done by using mass per unit length. Okay. Fine. I'll explain to him in Telugu. Mass per unit length ante ఒక యూనిట్ లెంత్కి ఎంత మాస్ ఉంది, ఎంత మాస్కి ఎంత లెంత్, అది రిలేట్ చేయడానికి యూస్ చేయొచ్చు దీన్ని. ఓకే. సో లాంబ్డా can be taken as dm by dl, small mass by small length. You can also write it as dm by dx. పవన్, ఈ కేసులో లాంబ్డా అంటే మాస్ పర్ యూనిట్ లెంత్ని టోటల్ మాస్ బై టోటల్ లెంత్ అని రాయలేము. ఎందుకంటే ప్రతి చోట డెన్సిటీ ఒకేలాగా లేదు, పాయింట్ టు పాయింట్ డెన్సిటీ మారుతూ ఉంది. సో టోటల్ మాస్ బై టోటల్ లెంత్ లాంబ్డా అనుకోవడానికి లేదు ఇక్కడ. సో స్మాల్ మాస్ బై స్మాల్ లెంత్, ఒక్కొక్క పాయింట్ దగ్గర లాంబ్డా చేంజ్ అవుతుంది కాబట్టి స్మాల్ మాస్కి మాత్రమే రాయగలుగుతాం. ఓకే. Others also listen. We can't equate this lambda to total mass by total length of the rod, because for the entire length lambda is not the same, not uniform. So we can only write it as small mass by small length at that particular coordinate. Okay. So you have to use lambda is equal to dm by dx. Then you get dm as lambda into dx. This is always true actually. Mass is mass per unit length multiplied with the length. This is generally true. In this problem, you are given that lambda is 2x, substitute it there. Therefore, dm becomes 2x dx. Pawan, did you understand?
Yes, sir.
Rishi, is this clear?
Yes, sir, I got it.
Okay, okay. Therefore, the x coordinate of center of mass can now be calculated as x into dm is 2x dx divided by integral dm. Also, you'll have to do integral 2x dx. You can't just write total mass because we don't know the total mass of this rod. Okay. And you can cancel terms only after integrating. Before integrating, don't cancel x like this. Okay, the answer will change. X is a variable, you can't cancel it like that. And you want to find out the center of mass of this entire system, which is the rod, right? Rod extends from x equal to 0 to x is equal to 2. So the limits for integration will be from 0 to 2. Okay. numerator there is a 2, denominator there is a 2. 2 is a constant, you can put it outside the integral, it will get cancelled. Let it be. Numerator, you have integral x square dx. Pawan, tell me what is integral x square dx?
X cube by 3.
X cube by 3. So the numerator becomes x cube by 3 with limits from 0 to 2. We still have to substitute that. Divided by denominator is integral x dx. Aishwarya, what is integral x dx?
Sir, x square by 2.
X square by 2. Substitute limit 0 to 2. Okay. 2 cube is 8. 8 by 3 minus 0 cube is 0. 0 by 3. That's the numerator. Divided by denominator. 2 square is 4. 4 by 2 is 2 minus 0. Answer is 8 by 3 by 2. That is 4 by 3 meters. 1.33. And as expected, the right half of the rod is heavier. Okay. I mean, the particles get denser as you move to the right side. So we expected the center of mass to lie somewhere to the right of this point. Midpoint is x is equal to 1. That is not the center of mass this time. It's 1.33. Okay. Aishwarya, good, you solved it on your own. Yusuf, that's fine. You try to follow from, like I know you just joined, try to follow from now onwards. This thing you can go through later. Pawan and Rishi, is this clear?
Yeah,
Yes.
sir.
Since it's a linear mass distribution, remember this in general. Whenever it's a linear mass distribution, mass of an element can be taken as mass per unit length multiplied with the length of the element. That's all. For linear mass distributions, you use mass per unit length. That's the idea. Okay. Fine. Now we'll discuss one more idea and then we will derive the position of center of mass of few other systems. Okay. Suppose there is a, fine, let's say there is a line like this. Consider one particle here and one particle here. Let's say they have the same mass. If two particles have equal mass, where does their center of mass lie? Anyone? Where does the center of mass of two equal particles lie?
At the
Middle, sir.
midpoint.
Midpoint. Okay. Center of mass divides the line joining 2 points in the ratio m2 is to m1 from the side of m1. If masses are equal, it will be their midpoint. Okay. So for these two particles, this is the midpoint. So that is the center of mass of these two particles. Okay, I'll mark it in black itself. Fine. Now consider two other particles, maybe one here and one here. They are equidistant from this line. Okay, symmetrically arranged. Where will the center of mass of those yellow dots lie? It will be here. Yellow particles, it will be here. Okay. Similarly, you can consider as many particles as you want, symmetrically arranged. Fine. I'll take one particle here and one particle here. For these two red ones, red or maroon ones, the center of mass is here. Okay. Now you consider all 6 particles as one system. For the red dots, the small red dot on that line is the center of mass. For the yellow particles, the small yellow dot is the center of mass. For the black particles, the small black dot is the center of mass. Now you can treat these 6 particles as a combination of 3 systems. Okay. This is one system. This is one system. And this is one system. And how do you find out the center of mass of a combination of systems? You treat each system as a single particle placed at its center. So the center of mass of all 6 particles together is nothing but the center of mass of these 3 particles. And it will lie somewhere on this line. Okay, do you all agree with this or not? The overall center of mass of this system has to lie on that gray dotted line. Yes or no? Okay. Just a moment. I don't know why it got disconnected. Yeah, so let me repeat my question. The center of mass of all these 6 particles combined lies on that gray dotted line. Do you all agree with this or not?
Yes, sir.
It does. One second. Now, this gray dotted line that I have drawn here is nothing but a line of symmetry for this system. Can any of you tell me what line of symmetry means? Generally, what is the meaning of line of symmetry of a system?
So like both sides it's identical.
Yeah, you should say one side is the mirror image of the other side. Okay, you call such a line as a line of symmetry. So what we can understand from all this is, if a system has a line of symmetry, then its center of mass must lie on that line. Okay, where exactly on that line we'll find out, but it must definitely lie on that line. See, I've taken 6 random particles here. I mean, not completely random, but I have taken 6 particles such that there is a symmetry. And we understand that for every symmetric pair of particles, the center of mass lies on the line of symmetry. Then for the entire system also, it should lie on that line of symmetry. Okay. Do you all agree with this or not? Is the idea clear?
Yes, sir.
Okay. So suppose there is a square frame. Where will its center of mass lie? Yusuf, can you tell where will the center of mass of a square frame lie?
Is it like hollow inside?
Where exactly?
So then it will be outside the ring, but inside the outside the circle, but inside the the top of the. So I can show it with my mouse, but I can't really explain where it is.
No, okay, let me mark the corners. Now I think you can describe the position.
So between C and D, I mean DC.
Why
on top.
will that point, which is the midpoint of C and D, become the center of mass? Okay. See, it's a continuous mass distribution. There are infinite number of particles in this. If you want to find out the position of its center of mass, you can do calculations and find out. But you can also make use of the idea that we just discussed. If a system has a line of symmetry, then its center of mass must lie on that line. Yusuf, tell me, does a square frame have line or lines of symmetry?
Yes, sir.
It does. How many lines of symmetry can you visualize for this?
So 4.
4. Can you describe? I'm sure one of them will be this. How will the other lines be? Other lines
Sure.
of symmetry.
So cutting it.
Cutting it in like upper half and lower half. Cutting it
Yes, yes,
horizontally.
sir. Cutting
Okay.
it horizontally.
And
So then diagonals.
diagonals. Good. Good. Now we just discussed that. In fact, we just proved that if a system has a line of symmetry, center of mass should lie on that line. Now this is one of its lines of symmetry. Then center of mass could be anywhere on this line. Maybe here, maybe here. We don't know the exact position yet. That is what we are trying to ascertain. Okay, I'm telling this to all of you. Now, since it's a square, it has some more lines of symmetry also. Even this is a line of symmetry, cutting it into two equal halves horizontally like this. Now, if this is a line of symmetry, then center of mass should lie on this line also. It should lie on the gray line. It should also lie on the blue line. Then it's clear that this point is the center of mass of the square frame. It's not necessary that center of mass actually has mass. Center of mass is just a point within a system. Mass need not actually be present there. Okay, see, this is a square frame. Mass is present only on this boundary. Fine, inside it is empty, but the center of mass is inside. So we made use of symmetry here. Now, suppose there is a circle. Where will its center of mass be? Tell directly. Aishwarya, where is the center of mass of a ring like this, complete ring?
The middle.
Center of the circle itself. Okay. Why? Because circle has infinite lines of symmetry. Every diameter is a line of symmetry. One like this, one like this. Any number of lines, any line, any number of symmetric lines you draw, they'll all have one common point, and that point is the center of the circle itself. Then that itself becomes the center of mass. Okay. So if a system has one line of symmetry, center of mass will lie on that line somewhere. If it has multiple lines of symmetry, then their point of intersection has to become the center of mass. Okay. And when we say symmetry, that symmetry should be in terms of mass distribution, not just the shape. What do I mean by this? Now see, we took a system of 6 particles like this. Let me copy this diagram. We took a system of 6 particles like this, which had a line of symmetry. How did we prove that center of mass lies on this line? For the red dots, center of mass is here. For the yellow dots, yellow particles, not dots, the center of mass is here. And for the black particles, the center of mass is here. But how did we find this out? We assume their masses are equal. Okay, black and black have the same mass, yellow have the same mass. Then the center of mass is the midpoint. That is how we found out that the center of mass lies on this line. Okay, so mass distribution should be symmetric. Okay, and what am I trying to say here? What I'm trying to say here is shape being symmetric is not enough. Mass has to be symmetric. What I mean is, suppose this yellow particle has 1 kg mass and this yellow particle has 2 kg mass. Then their center of mass will not be the midpoint. It will favor the 2 kg. Then the overall center of mass will not lie on this line. Shape wise, there is symmetry. Red dot, yellow dot, black dot. Red particle, yellow particle, black particles. So shape wise, there is symmetry, but mass wise, there is no symmetry. In that case, center of mass won't lie on the line of symmetry. Okay, we can't say. So only if you are sure that mass distribution is symmetric. Okay, mass distribution on one side should be mirror image of mass distribution of the other side. Then you can tell for sure that the center of mass will lie on the line of symmetry, somewhere on the line of symmetry. Okay, remember this idea. If there are multiple lines of symmetry, like in case of a square plate or a square frame or a circular frame, it could be a plate also. If there are multiple lines of symmetry, wherever those lines intersect, that has to become the center of mass, because it should lie on this line of symmetry. It should also lie on this line. Then their common point itself will be the center of mass. Fine. We'll be using this idea also in the derivations that follow. So apart from the calculation part, there are 2 ideas we learned about center of mass. Last class, we learned how to find out the center of mass of a combination of systems. Each system will be treated as a particle kept at its center. Okay. Then we'll treat them as collection of particles and solve. This class, one other idea we learned is, if a system has a line of symmetry, center of mass will lie on that line. Okay. Now for a full circle, we know center itself is the center of mass. Suppose you are given a system like this, center of mass of a semi-circular ring. See, in all these derivations, it's not the final result that is important. How we are approaching, how we are solving is what is important. So suppose there is a semicircular ring, which is basically nothing but half circle like this. We have to find out where its center of mass lies. And I have to tell you that it is a uniform semicircular ring, means all particles have the same density. So left half, right half, symmetry is there. Okay, all particles have the same density. We have to find out where its center of mass lies. You can assume its mass is m, radius is r. Total mass is m, and the radius of the semicircular ring is r. Pawan, tell me, does this system have a line of symmetry?
Yes, sir.
Can you describe that line?
Sir, vertically.
Vertical, y-axis, passing through the topmost point of that semicircular ring is a line of symmetry, correct? And what is the use of line of symmetry in center of mass problems?
We can find out its center of mass.
How
అంటే
do you
ఎక్కడుంటో చెప్పగలుగుతాం సార్.
డైరెక్ట్ చెప్పేసావా?
లేదు సార్.
That's what I'm asking. What is the use of line of symmetry? The use is that center of mass lies somewhere on that line. That much we can say. Where exactly it is, we can't say, but it will be on that line is what we can say. Now, I hope all of you understand that this is the line of symmetry for this system. Left hand side or left side of that line is a mirror image of the right side. Okay, so center of mass will lie somewhere on that line, and that line is the y-axis. Okay, for convenience, let's consider x-axis here. Okay, now we know center of mass lies on the y-axis. So what we need to find out now is the y coordinate of the center of mass. Fine. Follow this derivation very carefully, all of you. As I said, this is very important, and we'll be using these ideas in the concepts that follow also. In fact, in this chapter itself, there is something called moment of inertia, which we'll be deriving for different shapes. How we approach that will be similar to this. Okay. And next chapter, gravitation, electrostatics, fluids, in almost every chapter that follows, we'll be using these ideas. Basically, what we learn in these derivations is how to take an element in a situation and how to integrate based on that. Okay. Now, this is a continuous mass distribution. One of you tell me, what is the formula for YCM, y coordinate of center of mass, for a continuous mass distribution?
ydm by yd y
Tell properly, tell completely.
integral of ydm by integral of dm.
Integral y dm divided by integral dm. Now, how did we apply this to a rod? We selected a particle first. We called its mass as dm. We took its x coordinate and we called its length as dx. Okay, in case of rod, it was easy. Rod was completely along the x-axis. Now, this is a two-dimensional shape. Okay, x and y axis. It's in the xy plane. See, it's a linear distribution only. Mass is along a particular length, but it's a curved length, not straight. Fine. So remember, semicircular ring. See here, for our understanding, I have shown you the thickness. I have shown it to you as a thick ring. Actually, that thickness is negligible. Okay, we don't consider the thickness of the semicircular ring. So it's like a wire only, a thin wire which is bent in the shape of a semicircle of radius r. So it's still a linear mass distribution. Okay. Now what we need to do, we have to consider an element and we have to call its mass as dm and its y coordinate as y. Okay, let's try doing it that way. You take an element of this ring like this. Let the mass be dm. That's fine. You can see that this particle element has a particular y coordinate from here to here. Okay. Now, if you want to actually integrate this, you will have to express dm in terms of dy. Can one of you tell me the meaning of dm?
Sir, the mass of that small
Element.
part.
Correct. What is the meaning of dy?
Sir, the coordinate of the small part.
Coordinate is y. Generally, I'm asking you, forget small part and all, what does dy mean?
Change of y with respect to x.
There's no change with respect to x. I didn't ask you dy by dx. I just asked you dy. It's a small change in y. Okay. I'm telling this to all of you. Dy means a small change in y. Now see, y is nothing but the y coordinate. It's the vertical distance. Then dy should be a small change in the vertical distance itself. You can't call whatever length you want as dy. Once you called a particular distance as y, change in that only should be called dy. Now, why is all this important here? You look at the element, how it is arranged. Just a moment. The element that we have chosen is along this semicircular ring, right? It extends from here maybe to here. It's a curved element actually. Its length, let's call it as dl. It's a small element only. Let's call the length as dl. Its mass is dm. Let it be. But you can't call its length as dy because this is dy. dy means change in y. So you can't call that slant length as dy. You have to call this vertical length as dy. Now you look at the diagram and tell me, or you use your own logic and tell me, any of you, is dy same as dl? Is dy the same as dl? Just from visual inspection, when you look at it, do they appear to be same?
No, sir.
They are not same. Okay. Think of it like this. Consider a thin ring. Let me enlarge this. No problem. We'll discuss this derivation very slowly. It's important to understand why dy is not same as dl, how to connect them and all. This is the length, slant length that we are taking. And this is the vertical length that we are taking. How can these two be same? They are not the same. Slant length is definitely more than the vertical length. Pawan, do you agree with this or not?
Yes.
Okay. And there's no fixed relation between them also. See, for this vertical length, this is the slant length. Okay. You take the same vertical length somewhere below. Okay, I'll just copy paste this arrow as it is, dy arrow. If we take the same vertical length here and look at the corresponding slant length, here the shape is not that slant. This dl, okay, let me call it as dl1 here and dl2 here. Which dl is longer? dl1 or dl2?
DL1.
dl1 is longer. Okay. So as you go up, the slant length for a particular vertical length will be more. Fine. So there's no definite relation between dy and dl for a curve like this. Okay. And it's difficult to establish a relation between them also. Fine. Now, why are we even bothered about all this? Because what we want is the position of this semicircular ring. And to do that, we have to do integral y dm divided by integral dm. For that, we need to express dm in terms of dy. Now we know how to express mass of an element in terms of length of that element itself. We can express dm in terms of dl if you want. How to connect dm and dy is what we are trying to do, thinking about now. Okay, so if you can connect dy and dl, then you can connect dm and dy. But establishing a relation between dy and dl is difficult, because from level to level, at one level there's one dl for one dy, at another level there's a different dl for a dy. Okay, so there's no fixed relation between them. So in such cases, okay, what we do is we change the variable. We try to look at it in a different manner. So listen, all of you. Mathematically also, let me explain what we just did. I mean, what we are unable to do actually. This is a wire bent in the form of a semicircle. What is the total mass of the wire? M. And the radius of the semicircle is R. Now you all tell me, if radius is R, how much is this total length? How much is the total length of this wire? A semicircular ring. Rishi, what is the length of the semicircle?
Yeah, sir.
Pi r, half of a circle. Total length, pi r, you can call it as L. You know total mass, you know total length. And it's a uniform semicircular ring. I told you this in the beginning itself. The particles are all identical. Density is same everywhere. Therefore, we can write that the linear mass density of this system, linear mass density means mass per unit length, is total mass by total length, which is also equal to small mass by small length. So this is known to us. We can say that dm is equal to lambda into dl. So we can establish a relation between mass of an element and the length of that particular element. But that is not what we want to integrate. In order to perform this integral, we need a relation between dm and dy. And that is what we are not able to connect now. Okay. So for that, what we do is we look at things in a different manner. We assign length and this height by taking help of another variable. Listen, all of you, whenever you have curved distributions like this, one thing you can try to do. See, this is the element that we are considering. Connect the ends of the element to the center of the curve. Now it's a very small element actually. For us to be able to visualize, I have shown significant size of the element, but that element is actually very small. Now when you connect the ends of the element to the center of the curve, those lines will subtend an angle theta, and the lines will have a small angle d theta between them. Let them have. Okay. This is the length of the element that we have considered dl, and this is the y coordinate of the element that we have considered. Okay, y coordinate, and it will have a small change in y coordinate also, dy. Listen, this the mathematics that we do here is very important. We had to express dm in terms of dy. That is the problem that we were having. So now we will take help of this theta. Now see, it's a semicircular ring. This length dl that is there is actually in the shape of an arc. Can one of you tell me the relation between length of an arc and the angle it subtends at the center of the arc? How are length and angle subtended by an arc related? When we discussed plane angle, we had used this. Even in circular motion, we had discussed this. Yes, Pawan, you unmuted.
L is equal star theta.
L equal to r theta, correct. Length of the arc is radius multiplied with the angle it subtends. So Pawan, tell me, what is the relation between dl and d theta, small length and small angle? Okay, it will be dl is equal to r times d theta. Okay, I hope this is clear to all of you. Even in circular motion, we had used L is equal to r theta. Differentiate this, you will get dl by dt is equal to r times d theta by dt. dl by dt is nothing but the speed of the particle moving along the circle, and d theta by dt is nothing but omega. We had v is equal to r omega. Okay, so length of an arc and the angle subtended by it are related as L is equal to r theta. If it's a small length, small angle, then small length is equal to r times of small angle. dl is equal to r d theta. Okay, so understand what we are doing here. We are changing the variable. The L term is being converted to theta terms. Why? Because if you do that, it will be easy to express dm in terms of dy. Okay, let's see. We still haven't come to that point. Now you all tell me, r is the radius of this semicircular this thing that we have, ring that we have. Let's call the center as O. Call this point as P. O to P, the distance is r. Can one of you tell me how much is y in terms of the radius? Radius and theta. You can use r and theta. Tell me y in terms of r and theta. You can think of it like this. I'll help you with the visualization. This is r. This angle is theta. This is the y coordinate. How do you how do you relate r, theta, and y is my question. It's a right angle triangle. Relating two sides of a right angle triangle is a anyone relation between y, r, and theta? I don't know why it got disconnected in between. Pawan, unmute.
Yes, sir.
Which is the hypotenuse in this right angle triangle? Which side?
R.
Okay. Now theta is shown outside the triangle. Is theta one of the angles inside the triangle also or not?
Yes, sir.
Which angle?
Sir, y opposite only.
Opposite to y, correct? This angle is theta. So for the angle theta, y is the opposite side and r is the hypotenuse. Why are you not able to relate them? Which trigonometric ratio relates opposite and hypotenuse to the angle?
Sin theta.
Sin theta, that's all. So sin theta is opposite divided by hypotenuse. So y becomes r sin theta, that's all. You can also say y is nothing but the y component of r. R makes an angle theta with the x-axis. So x component will be r cos theta, y component will be r sin theta. Is this clear to all of you? Yusuf, did you understand? Rishi?
Yes, sir, understood.
So y is equal to r sin theta. Let us make use of that also. Now, from element to element that you take, okay, our aim is to find out the center of mass, no? So we'll be considering all elements of this system. As you move from element to element, is y going to change or not? Any one of you can answer. When we move from one element to another element, will their y coordinates change or not?
They will, sir.
Definitely. And as you move from element to element, will theta also change or not? it will change. Okay. For the first element here, if you see this one, theta is 0. For the upper element, it is pi by 2, 90 degrees. For the last element, it is 180 degrees. Okay, or pi. Okay, element to element, theta will change, y coordinate will also change. Okay. Now, again, let us keep our target in mind. Our target is to integrate y dm. We know how to express dm in terms of dl. Okay, dm is equal to lambda into dl, that is established already. But that's not needed now. We need dm in terms of dy, not in terms of dl. And we were not able to express dm in terms of dy. So what we did is we changed dl to d theta terms. Next, we will change dy to d theta terms. Then we will relate them. That's the idea. Okay. Now we have y is equal to r sine theta, where from element to element, y is a variable, theta is also a variable. So there are two variables in this. We need a relation between dy and d theta now. Y is equal to r sine theta. We need relation between dy and d theta. So we will differentiate this equation. Simple differentiation. You can differentiate with respect to any variable you like. Y and theta are variables, no? Let us differentiate it with respect to theta. It's your choice. You can differentiate with respect to y. You can differentiate with respect to theta. You can differentiate with respect to time, any variable you like. Okay. I'll differentiate with respect to theta. So I'll get dy by d theta. That's the derivative of the left-hand side is equal to r into, one of you quickly tell me how much is the derivative of sine theta with respect to theta?
Cos theta, sir.
Cos theta. The right-hand side becomes r cos theta. Therefore, dy is r cos theta d theta, and there we have it, the relation between dy and d theta. Now, what is the use of all this? As I said, you have to keep the target in mind. We had to integrate y dm divided by integral dm. Integral dm is total mass, that's easy only. To integrate y dm, we are struggling. Now, that struggle is gone. We can express y as r sine theta. Okay, that's from this triangle we got. So y, in place of y, I am writing r sine theta. And what about dm? Dm is nothing but the mass of the element. We know dm is equal to lambda dl. That is generally true for any linear mass distribution. Dm is equal to lambda dl. We got dl as r d theta. We will make use of that now. So in place of dm, I am substituting lambda dl, and that is nothing but lambda into dl is r d theta. Okay, actually in this derivation dy is not necessary. Let us leave it. Unnecessarily we found, but okay, no problem. Divided by integral dm. Integral dm will be the total mass of the semicircular ring. Let it be. Okay, so hope you all understood. This part is y and this part is dm. We were unable to express dm in terms of dy. So what we did is both of them we converted to some other variable. Y was expressed in terms of theta, dm was expressed in terms of d theta. Now, the only variable in this complete integral is theta. Other terms are constants. Let's put them outside. R lambda divided by m will be outside. You will be left with integral sine theta d theta. And to cover the entire semicircle, theta should go from 0 to 180 degrees. Or in radians, it should vary from 0 to pi. Then the entire semicircle will get covered. So those are the limits that we are going to use. 0 to pi. Okay, one of you quickly tell me what is integral sine theta d theta?
Minus
Integral,
cos theta.
good, minus cos theta. I'll put the minus outside. cos theta inside. We still have to substitute limit 0 to pi. So that becomes minus r lambda by m cos pi. Cos 180 degrees is minus 1 minus of cos 0. Cos 0 is 1. Minus 1 becomes minus 2. Minus and minus cancel. You get the answer as 2r by m into lambda. What was lambda? Total mass by total length. Now the radius gets cancelled. Wait, how did radius get cancelled? Just a moment. Okay, there are two r's. No, it is r square lambda by m. Fine. Because like why I got this thought that radius cannot get cancelled is because we are trying to find out the y coordinate of center of mass. Y coordinate is supposed to be a distance. How can there not be a distance in the answer? Okay, there has to be a distance. So there's r square here. Square and r get cancelled, m gets cancelled. You will be left with 2r by pi. Okay, this result you will find in all the books, but you should know how it is derived also. Derivation also you'll find in most books. Pi is 3.14. Okay, so 2r by pi, 2r by 3.14. It's a value less than r. Value less than r means less than the radius. Now, we knew that center of mass would lie on the y-axis. This is y is equal to 0. This highest point is y is equal to r. Center of mass we found out is at 2r by pi. Okay, just a moment. 2 by pi, 2 by 3.14 is how much approximately? 0.64. So the center of mass lies somewhere here at a height of 0.64 times the radius. That is what we found. Okay, so let me take you through this derivation once again quickly. You were given a semicircular ring, which is obviously a continuous mass distribution, and you are asked to find out where its center of mass lies. First, we identified that this system has a line of symmetry, y-axis. So we confirmed that center of mass should lie somewhere on the y-axis. Okay, so all we need to find out now is the y-coordinate of center of mass. For a continuous mass distribution, this is how you find y-coordinate of center of mass. Integral y dm by integral dm, where dm is the mass of an element and y is its y-coordinate. But when we visualized an element and its y-coordinate, we ran into trouble. The problem was that it was difficult to express mass of the element in terms of the height dy. We can express mass in terms of length dl, but expressing it in terms of dy was the trouble. So what we did is we took help of theta. We called this angle as theta. Then the y-coordinate changed to r sine theta, and dl changed to r d theta, and then our problem was solved. Mass we expressed in terms of theta, y-coordinate also we expressed in terms of theta. Now there's only one variable, we could easily integrate. That's what we did effectively. Okay, in between unnecessarily we derived dy actually. For this derivation, it's not necessary, but there are some cases where you will need that also. Okay. Fine. Some of you may not have noted this. That's okay. I'll send you the notes. Try another problem now. In this question, you were given a semicircular arc. Instead of a semicircle, okay, suppose you are given something like this. Let me test how much of this you'll be able to apply. Okay, instead of a complete semicircle like this, okay, let me remove some part of it. Right. The radius is still r, but the problem now is that this is not a complete semicircle. It extends only up to maybe 37 degrees on the other side. This side is 90 degrees, that side is only 37 degrees. derive the position of its center of mass. I'll give you some hints. You know it's a continuous mass distribution. This time, the y-coordinate is not even the line of symmetry. Neither is the x-coordinate, nor is the x-coordinate the line of symmetry. This system does have a line of symmetry, like this, but it's of no use. It's not the y-axis, it's not the x-axis. Okay? So, you will have to find out y-coordinate of center of mass. You'll also have to find out x-coordinate of center of mass. But let's do it step by step. If you want y-coordinate of center of mass, you know what you need to do is integral y dm divided by integral dm. Okay. Assume mass per unit length lambda is given to you. Radius is r. Mass per unit length is lambda. Now, why I am giving you lambda and not expecting you to calculate is because in the previous situation, it was a semicircle. Okay, now also actually it need not be given. You can calculate, but okay, keep it as it is. In the previous situation, it was a semicircle. So we did m by pi r because length of a semicircle is pi r. Now lambda will be m by this length, which is not even pi r. Okay, so don't bother about that length. Keep lambda as it is in your derivation. That is what I'm trying to say. Actually, you can tell that length because you know the relation between length and angle subtended, no? You can use L is equal to r theta and find out the actual length of this also. Okay, in JEE advanced problems, you are expected to do all that on your own. But for now, the application of what we learned in the previous derivation is what we are checking. So try this, all of you. Find out the y-coordinate of center of mass and then find out the x-coordinate of center of mass. First, work on the y-coordinate. So you know what to do. Okay, why did I erase the element? Let this be the element. Its length is dl. Angle made is theta. Small angle is d theta. This is the y-coordinate. This is the radius. Try. Okay. Any answer for the y-coordinate, anyone? Right. Venla, can you unmute?
Yes, sir.
So, where did you get stuck?
The lambda is getting cancelled for now, that's why. I think it's wrong.
Lambda can get cancelled. Let it be, but did you get any answer in terms of r?
3r by 5.
3r by 5. We'll see. We'll see. But tell me what all you did. What is y equal to? Like, you can't express dm in terms of dy directly. That is difficult. So we change the variable. We express y in terms of theta and dm in terms of d theta. So Vanilla, tell me how much is y or what is y in terms of theta?
R sin theta, sir.
Y is r sin theta itself, just as we took in the last derivation. Okay. And what about dm?
Alpha d theta, sir.
What is alpha?
Lambda d theta.
Dm is not lambda d theta. Okay. Listen, I'm telling this to all of you. Lambda is linear mass density, means mass by length. Okay. So lambda or dm will be lambda into dl only, length of the element. Okay. But dl can be written as, dl is nothing but an arc. Okay. Small length of the small arc. dl becomes r d theta. So dm becomes lambda r d theta. That is what we did in the last derivation also. Hope this point is clear to all of you. If you have a doubt in this, you can ask. Okay. So dm is lambda r d3. We got y in terms of theta and dm also in terms of theta. We will now be able to substitute them and integrate. Okay. So it becomes integral r sine theta, that is y, and dm is nothing but lambda r d theta divided by integral dm becomes the total mass. Okay, let it be as it is as of now. Or you can do integral dm also as integral lambda r d theta. Okay, and as Vanilla was saying, lambda gets cancelled. It's a constant. Constants can be cancelled before integration itself. No problem. One r also can be cancelled. D theta you should not cancel, okay? Theta is the term with respect to which you are integrating. That cannot be cancelled. Fine. So r stays outside the integral. Numerator you have integral sine theta d theta. Denominator you have simply integral d theta. Integral sine theta d theta we know is minus cos theta. Limits will be from 0 to, okay, see, for this element the angle is 0, and for this element it is 90 degree plus 37 degrees. Okay, so 0 to 90 plus 37 itself I'll write, because we know what to do with cos 90 plus theta. Denominator integral d theta is nothing but theta. Here also same limits, 0 to, you need to be careful here, you can't take 90 plus 37. You have to substitute it in radians, not in degrees. Okay, so okay, I'll just write it as theta final. Doing that might have been difficult. I'll teach you how to do that also, no problem. So put the minus aside, the answer becomes minus r into cos 90 plus theta. Anyone? Or cos 90 plus alpha generally, how can you express it?
Minus sine theta, sir.
Minus sine alpha. Okay, so this becomes minus sine 37. Sine 37 is 3 by 5, so minus 3 by 5. And minus lower limit also you have to substitute. Cos 0 is 1 divided by theta final. Okay, yeah, this part is slightly difficult here. Maybe if I had given 30 degrees, it would have been easier, but let it be, not an issue. Minus 3 by 5 minus 1 is minus 8 by 5. Minus minus gets cancelled. Numerator is 8r by 5 divided by that final angle is still there. In radians, you have to substitute. Now, what is the actual angle? 90 plus 37, 127 degrees. We know 180 degrees is pi radians. So 127 degrees is how many radians? Is what we need to find out. Divide them, you'll get. So theta final becomes 127 by 180 into pi. That you will have to put here. So answer is quite complicated, but this is how it is done. Is the procedure clear to all of you? It's the same as what we did in the last problem. Only the integration with limits was difficult. Substituting limits was the difficult part. Because in the last problem, limits were from 0 to 180. It got cancelled quite easily. Okay, in this problem, the limits are 0 to 90 plus 37. That's the only difficult part. Is this clear to all of you? Yusuf, did you understand? Pawan, if I give you some other angle, will you be able to find out the center of mass? Pawan.
Yes.
Okay, just limits. You just have to adjust the limits. Okay, so this way we get the y coordinate of center of mass. All that is fine. Let's also think of what to do about the x coordinate of center of mass. Okay. First of all, Rishi, tell me the formula for x coordinate of center of mass in a continuous mass distribution.
Integral of x dm by integral of dm.
Okay. So instead of y, this time you have to integrate x dm divided by integral dm. Now again, from element to element, the x coordinate also will vary, and it will be difficult to express mass of the element in terms of dx. This is x, and that small width will be dx. But that small width dx is not the length of the element. So we can't directly relate dm to dx. So we will again have to rely on theta itself. This time we'll have to express x in terms of theta and dm in terms of d theta. Dm in terms of d theta has already been done. Dm is lambda into dl, and dl is nothing but r d theta. So dm being expressed in terms of d theta is done already. Okay, Vanilla, don't answer. Others, any one of you tell me how to write x in terms of theta. You can recollect how we wrote y in terms of theta if you want. On similar lines, you tell me how to express x in terms of theta.
Sir, x is equal to r cos theta.
Good. X is nothing but the x component of radius. Okay, so x will be r cos theta. Fine. So the integral will now become r cos theta into lambda r d theta divided by integral dm. Integral dm is integral lambda r d theta. Just adjust the limits. I mean, substitute the limits carefully, you will be able to solve it. Okay, I understand substituting limits and final answer are quite complicated. Let it be. But I hope you got the idea of how to approach such problems. If there is a curved distribution like this, you can take help of arc and the angle subtended by it. That is the idea that I wanted to convey. Okay. So this is a continuous mass distribution. In fact, it's a linear mass distribution. Linear doesn't always mean a straight line. Curve is also a linear distribution only. Okay. It's like a bent wire. Fine. So we are using mass per unit length, and to express dm, we are using lambda is equal to dm by dl. So dm becomes lambda dl, where dl is the length of that element. But we want to express it in terms of theta. So dl is written as r d theta. Okay. Fine. So for a semicircular ring, the center of mass is at a height of 2r by pi. You need to remember this result. You have to memorize it. And it is better if you derive it also. Now see, what have I done here? I took angle theta with the x-axis and derived. Okay, you all are comfortable with this now. What I suggest you do is, same diagram, assume theta is the angle made with the y-axis, not the x-axis. Take this angle as theta. Okay, then what will y become? Y will become r cos theta this time. And the limits will change. For this element, theta will be 90 degrees. For this side element, last element, okay, wait, clockwise angles minus anti-clockwise angles positive. So the right side extreme is minus 90 degrees, left side extreme is plus 90 degrees. Those will be the limits this time. I want you all to try to derive it like this. Okay, I'll draw this diagram and send you in tomorrow's worksheet. Worksheets based on center of mass are compulsory. If you don't solve them, don't attend the next class. Okay, and you will definitely get the worksheet by tomorrow afternoon. Sit and solve it, complete the worksheet by tomorrow evening and send it to me. Because as I said, these ideas are going to be used repeatedly, and I'm not just me, no teacher will teach all these repeatedly. Okay, once you learn this, you apply it in other chapters directly. And it's not the final result that you have to remember. How we are choosing the element, how are we substituting terms in the integral, how are we converting variables from one to the other. In place of y, we are writing r sine theta, means we are changing the variable altogether. Okay, those are the ideas that you need to get a grip of. Okay, just 10 more minutes. We'll just I'll just introduce another system to you. We'll not do the derivation, but we'll just think of some steps to do it. Suppose there is a semicircular disk. Okay. Can one of you tell me what's the difference between a ring and a disk? What's the difference between ring and a disk? Yeah, Yusuf, what you said is correct only. Rishi, what is the difference between a ring and a disk? Okay, Pawan, difference between a ring and a disk.
సార్ రింగ్ అంటే ఒకటి కార్నర్స్ అంటే ఎడ్జెస్ మాత్రమే ఉండదు, కానీ డిస్క్ అంటే మొత్తం అంతా ఫ్లాట్ కూడా వచ్చేస్తుంది.
Okay, ring is like a frame actually. Mass is there only on the boundary. Disk has mass all over it. Okay. Now one of you tell me this. Ring is a linear mass distribution. It's a wire bent like a semicircle. Okay, wait. Ring is a full circle, no? It's a wire bent in the shape of a circle. It's a linear mass distribution. What kind of mass distribution is a disk? What kind of mass distribution is a disk? Okay, see, there are three kinds of mass distributions: linear, aerial, volumetric. Now you tell me what kind of mass distribution is a disk? Is mass spread over length? Is mass spread over an area? Or is mass spread over a volume in a disk?
Sir, length.
How? How do you justify that?
Sir, because in a disk, like the mass is like different and different parts of it. So
How are you saying mass is spread over a length in a disk?
It is spread over
Sir,
area, sir.
It is spread over an area. Like, see, there's no proof or anything for this. It is simply visualization. Can you bend a line and make it a disk? Is it possible? Can you bend a wire and make it a disk? No,
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 sir.
disk is a surface. Okay, disk has a surface. You can't simply bend a wire and make a disk out of it. Rishi, do you agree with this or not?
yes, sir.
Pawan, is it clear? Did you understand what I'm trying to say? You can cut a surface and carve a disk out of it. Yes or no? Pawan. You can cut a flat surface into the shape of a disk. Do you agree with that or not? Okay, fine. Disk is a surface mass distribution or an aerial mass distribution. If it's a full disk is like a circle on a plate. It has lines of symmetry. Center itself will be the center of mass. But suppose there is a semicircular disk like this. Semicircular disk is half disk. And we need to find out where its center of mass lies. First thing we concluded is that it's an aerial mass distribution. Means mass is spread over an area. You can't bend a line and make this shape. You can cut a surface and make this shape. Okay, so it's an aerial mass distribution. Rishi, tell me, does this have any lines of symmetry? At least one.
Yes, sir.
Yes, clearly the y-axis again, like the way this is arranged, the y-axis is a line of symmetry. Why do we bother about line of symmetry in center of mass problems? How does line
Because
of
the
symmetry?
center of
Ah.
it lies on the line of symmetry.
The center of mass would lie on the line of symmetry. That's why we look for lines of symmetry. Are there any other lines of symmetry, or this is the only one?
Only one, sir.
This is the only one. So we just know that center of mass should lie somewhere on this line. Where exactly, we can't say. Had there been two lines of symmetry, their point of intersection would have become the center of mass. But in this case, we can't identify another line of symmetry. So if you take the base as the x-axis and this as the y-axis, y-axis is the line of symmetry here. So again, what you need to find out is the y-coordinate of center of mass, which is integral y dm divided by integral dm. But in this case, it gets very complicated. Why? Can one of you tell me what dm means? What is the meaning of dm?
Small mass of the small particle.
Mass of a particle. Correct. This time, since it's an areal distribution, taking a particle itself will be difficult. Why? If it's a bent wire, small part of the wire can be considered as a particle, and we can write dm is equal to lambda into dl. The mass will have a certain length. This is an areal distribution. If you consider a small part of this area, okay, and call its mass as dm, it occupies an area here. That area is dA, small area dA. Okay. So we can express mass in terms of area. We can relate them. If full disk has a mass m, half disk will have a mass m by 2 in terms of area. 1/4 of the area will have 1/4 of the mass. So mass is proportional to area. So listen, in case of areal mass distribution, we use something called areal density. For linear distribution, we use linear density. For areal distribution, we use areal density, which is denoted by the symbol sigma, which is nothing but mass by area. You can also write it as small mass by small area. Therefore, the small mass dm can be expressed as areal density multiplied with area, sigma into dA. Okay, you'll get used to this, not an issue. But this won't be of any help in this case. Why? Because you need to integrate y dm, and to integrate that, see, we have considered a dm here, that's fine. Y is the y coordinate of the dm from here to here. This is y. How will you express dm in terms of dy? Very difficult. Okay, and in fact, this time there will be a number of dms, okay, infinite dms having the same y coordinate, like this. So you'll have to look at it in a different manner this time. Till now, what we did was we chose an element first, then we visualize the y coordinate. Now you have to do the reverse. Take the y coordinate first, then visualize the element. Okay. How? Fix the y coordinate. Let's say some height y is considered. Take all the mass that is present at that height. Means you will have to take all this mass. Between these two parallel lines. From that y coordinate to the next y coordinate, what all mass is present? All that mass is what you call dm now. And the height of that mass from here to here, that height is dy. Or I should say width maybe. Okay, that width is dy. to integrate this, you should express dm in terms of dy. Okay, so this requires some new mathematical ideas. All those will be discussed in the next class. So how to deal with, what is this, areal mass distributions is what we will learn in the next class. Okay, again, don't miss the class. You will have class on Wednesday. For today, we learned about linear mass distributions. In case of curved lens also, we learned how to deal. Okay, we take help of theta. Okay, next class, we are going to discuss this. In fact, I'll give you some ideas in the worksheet. If any of you are able to solve it on your own, solve it. Some of you may have done this in school already. Okay, just go through it once again so that next class will be much easier for you. But the problems that I give on linear mass distribution are compulsory in tomorrow's worksheet. Solve it and send the answers to me. Okay, because see, physics as a subject, it is like that. If you do not master one concept, understanding the next concept will be difficult. Okay, so you will have to spend time on this. I'll try to send the worksheet as early as possible tomorrow, but by tomorrow evening, you solve it and send it back to me.